Hi, welcome to Advanced Thermodynamics. And while it may sound like a boring and very abstract topic, it certainly is an abstract topic. But what I want to demonstrate in this course really is that it's also a very modern course. The very modern questions that we have as mechanical engineers right now, particularly concerning propulsion and power, we will really need to dive more and deeper into thermodynamics. So the way I plan to do this is from the angle of propulsion and power perspective. So let's start. In fact, let's start with two different machines, two different types of engines, and see how far we get just with very, very rudimentary analysis. So the two devices I'd like to start with are the diesel engine and the gas turbine. Now, we will focus really on fluid properties, fluid behavior. So this will not be about the cycle analysis of these things. But let's talk about how these engines work and what they do. Let's start with a diesel engine. Diesel engine is a piston engine. And what we need there is fresh air that gets pulled into the engine. It gets compressed then at the maximum compression, approximately. The fuel is injected because the compression is so hot. The fuel starts to burn without needing something like a spark plug, and then the combustion expands the gas inside of the piston and ultimately creates the force that we then convert to some torque at our wheels. So I'll not go through here all strokes of that, but let's just say we have certain airflow coming in. And our piston moves out. And then what we have is that our valves close. Piston moves in, the gas in here heats up, then fuel is injected, and then what happens is that this fuel burns and expands, and that is what propels our engine. So this is supposed to be some flame. The question that is most interesting to me here is, what is the state of that liquid jet? What is going on inside of that engine here, here, here? And what do we need to understand to be able to explain these things? So, piston engines. First thing to know here is that piston engines, such as diesel engines, are typically characterized in terms of a compression ratio. That is CR, and that is the ratio of the volumes. And what I mean by that, actually it's, yes. So we have volume 1 here in full expansion. And then volume 2 would be the volume that we have after compression. And high performance diesel engine could have something like 16 to 20. All right, let's now look at a gas turbine. Gas turbine, you're familiar with that from flying somewhere on an aircraft. That's what's hanging under the wings. And the way these work is very different. I'll not go through all the intricacies, so we'll not cover different types of gas turbines. So for example, practical engines nowadays have a very high bypass ratio. That means that most of the air is actually not going through the engine. But we're not interested here in the aerodynamics of how to build an engine, but really of the thermodynamics of what's going on inside. So we'll just focus on that. And what we have then is typically something like that, where we have some compressor here in the front, or fan. The air goes in here. You see it narrows down, and that is a compression effect. Whoops. Then we have that air as a combustion goes into a combustion chamber. Let's not talk about all of the details, but in essence also we have a fuel injection process here somewhere. One difference is that typically fuel is injected, it's pre-mixed with the surrounding, and the flame is someplace else. But nonetheless, we do have a fuel injection phenomenon or process into the compressed air. Then this burns continuously, and we have hot exhaust gas coming out in the end. And then here what we have is the turbine, where we extract some of that energy to ultimately drive the compressor in front. So the air goes through here, gets heated, and then we have some exhaust. So big difference to the diesel engine is of course that this is a continuous machine. In a diesel, it works intermittently in a cycle, or in cycles. In here, it works just continuously. Another thing is just nomenclature-wise, in the gas turbine world, we don't talk about a compression ratio, but we talk about a pressure ratio. Or the overall pressure ratio. And I'll get to that in a bit. But essentially what that is we have some pressure upstream here. And then we have a pressure here after compression. That's the pressure which the combustion occurs. And the pressure ratio then is just that. And for modern engines, the overall pressure ratio will be somewhere beyond 40, and modern engines maybe projected to something like 60 nowadays, but it's steadily increasing. So the question that I have now is, all right, so we can look up these numbers, we can look up the compression ratio, we can look up the pressure ratio for certain engines, but does that tell us what's going on inside of the engine? Well, let's just say, well, okay, we know the ideal gas law, the perfect gas law. That is, we have the pressure divided by the density equals the gas constant times the temperature. So for example, when we now look at a diesel engine, we know that we have a certain compression ratio. And as I said, that is the volume ratio. Now, as the cylinder is closed, the mass does not change. So we can factor out the mass here. same on both sides. We end up with a specific volume ratio, and that's just the inverse of the density ratio. So what we can do now is to plug that back into our ideal gas equation of state. And we can write for the pressure, that is the density to RT. We can use the compression ratio to change that and express that in terms of properties that we know from what's going on before the engine. That is the density at 1. And this is what we end up with. So we have a partial success. We can write a relation between the pressures and the temperatures after the compression, but we're not able to calculate that from first principles just by knowing the compression ratio. And the problem is that we have an infinite number of combinations of temperature and pressure that all fulfill this equation. So what we need to do next is to find a way, and a spoiler alert, it will be using thermodynamics, to actually get an expression that allows us to calculate what the temperature is and the pressure inside of an engine at the compression event.